In this particular part of the discourse, we will try to describe or undertake the discussion on wave propagation or little precise analysis of the wave propagation for different kinds of mediums. So, to begin with, let us recall that the way theory of electromagnetism, once it is introduced, then it is introduced in terms of electric and magnetic field vectors, and the action in the momentum space is given by what we are seeing in the slide. It is written as S naught. And other than the electric field vectors and magnetic field vectors defined as E tilde and B tilde, there are no parameters involved over there. So, if there are no parameters involved over there to describe temperature, then number density or other things, it can be very well assumed that this is a relation that holds good for electromagnetism in vacuum. There is one thing very explicit before us, the occurrence of the indices alpha on E as well as B, and a little tilde that is defined, let us put on the top of these two vectors, electric and magnetic field vectors. So, if we have to take this index alpha, then what are the values that alpha should in principle take? Alpha in principle should take values from 0 to 3, that means 4. And so does the magnetic field. But in reality, when we talk of electric field or magnetic field, we have only 3 components, and all 3 of them are spatial components. So, how do we come to the 4th component of the electric field vector and the magnetic field vector? So, we use a trick, and that trick is multiply the electromagnetic field tensor F mu nu by u. Here we have taken u lambda with F lambda nu, and for the magnetic field we multiply by u lambda 2 epsilon alpha beta lambda nu times F alpha beta, that is written on the bottom line. So, what does it yield, or what advantage does it give us? They are following: E tilde, its 0th component actually vanishes. And how does that vanish? Because in the rest frame of the system, u 0 is the only finite quantity, rest of them are 0. So, when you contract the index lambda, only the term for u 0 survives, and for u 0 in the product what survives is f of 0 nu. Now, when the moment nu is considered 0, the antisymmetric tensor has both the indices same. So, it automatically goes to 0. Therefore, E of 0 is 0, and we are back to a safer side. Similarly, for B tilde nu, as soon as u naught is finite, epsilon only retains terms 0 and alpha, beta and nu, and they are bound to take only spatial variable. And when they are bound to take spatial variables, by construction and identification with the vacuum case, we get B tilde 0 equal to 0 and B tilde x y z or 1 2 3 equal to the magnetic field in 1, 2 or third direction. So, this construction in terms of the medium velocity vector saves the grace of the day for us, and that is why the equation above that is displayed describes the vacuum electrodynamics perfectly well. And what else does these two relations do? These two relations between electric field and the field strength tensors basically provides the identification of the electric field and the magnetic field with the corresponding vector potentials. And their constructions are such that by construction they are gauge independent. So, what happens when you take the energy and momentum density of the system into account? This action that we had given before changes itself to an action where the quadratic part of the electric field is multiplied by something called epsilon, and the quadratic part of the magnetic field multiplied by something like 1 over mu. These factors, they are called permittivity and permeability. They are multiplying prefactors to the quadratic electric field and the quadratic magnetic field. And in principle, they can only be function of temperature or Lorentz invariant combinations of k, omega, etc. Those can be constructed by from the system variables like wave vector, the medium frame velocity and 4k square. And needless to say, the E tilde and B tildes are also present. Now, if we project the same thing and evaluate the same action by evaluating this particular Feynman diagram that gives us the self energy correction to photon, then we get a quantum action basically, which is given in terms of the gauge fields, the polarization tensor and the gauge field, the quadratic part in the gauge field, because there are only two gauge field, those are present in the diagram. The higher order parts in this series are essentially truncated, assuming that the fluctuations are not too large. And the factor of half here takes care of a situation when there is overcounting in the system. So, now if we compare these two situations where the electric field and magnetic field and their dependence on the medium has been taken into account by incorporating the permeability and permittivity, and that of the covariant situation that was given by in terms of the gauge fields A alpha and A beta. Then the quantum action actually can be written in this particular form, where the coefficient of the quadratic part in electric field and the coefficient of the quadratic part in the magnetic field can be related to the respective form factors and the wave vectors. And from here, if one tries to identify the full action, that is written in terms of epsilon and mu to that of the one that we have over here, then it turns out that if we define these factors epsilon and mu in the following way, that is epsilon of k omega can be related to 1 minus the longitudinal form factor over 3 vector square, wave vector square, and 1 over the permeability is in terms of the longitudinal, the transverse form factor, its energy, and the wave 4 vectors. Then they can be manipulated algebraically to give us pi L in terms of only epsilon and k square, 3 k square, and pi transverse in terms of epsilon, mu and 3 k square. Now, what we can do from here is we can define something which is 1 minus epsilon, and that will give us the longitudinal form factor upon the 3 vector k square, and similarly this 1 minus 1 over epsilon mu to be equal to rest of it, which is given on our right hand side. What we have not considered during this discourse so far is the form factor that is associated usually with what is termed as the third electromagnetic constant in some situation, or in the case where there is a magnetic field present in a medium, then it is called the Faraday term or Faraday effect, which is given by epsilon of p, that is equal to the form factor corresponding to the Faraday term divided by the wave frequency omega square. So, how does these terms essentially come into being or are realized for a theory under consideration? To understand that, we have to go back to the Feynman diagram, and instead of considering a 2-point function we have given here, we should be considering here a 3-point function, where you imagine that this another external photon line that has been inserted, and when the external line carries almost 0 momentum, why almost? It may carry 0 momentum, and that particular thing or magnitude of 0 momentum, due to that it is called a ultra soft line attached to this particular diagram. Then there are few quantum field theoretical theorems that starts coming up, and that dictates that this particular diagram to be invariant under charge conjugation symmetry. There must be some particular combination of the field strength tensor of the external photon line that was joined with zero momentum and the chemical potential of the system to talk of C invariance, and similarly one can talk of the other discrete symmetries that this particular diagram under that situation can contribute. So, the final result that follows from this exercise is the generation of a corresponding new finite quantity or new finite form factor that you have defined by pi of p, and the estimates of pi of p for different values of the parameters temperature, pressure, frequency, wavelength governs the propagation of the electromagnetic wave in a medium. In general, the gauge potential can sometimes be written in terms of the 4 current times the propagator delta of A B, but this form is not necessary right at this hour, and we can talk about it later. So, at this stage we are left with the form factors pi L and pi T. If we are not interested about any soft photon insertion to a fermionic bubble. So, how to get to these two objects pi L and pi T, that is the longitudinal form factor and the transverse form factors. Mathematically speaking, there are something called projection operators, and once one uses the property of the projection operators and multiplies the polarization tensor by them from left. So, they become actually equal to the form factors times some kinematical variables, and at last if the manipulations, that is algebraic manipulations, are performed properly, one lands up with pi L equal to what we have on the top line here, and pi transverse equal to what we have on the bottom line, where on the right hand side we have to subtract out half the longitudinal form factors magnitude from the trace of pi min. They behave, or their behavior in the ultra relativistic limit, that is what means that you can neglect the mass of the fermions compared to the other quantities those are present in your system parameters like temperature or frequency or wave vector, 3 wave vector. So, in this situation the real part of pi L behaves in this particular fashion, and if your energy is beyond the pair production energy, then the imaginary part is 0, and so do is the transverse part of the form factor, which is given in the line below. In the static limit, they give expressions what I have given here, that real part of pi L, that is a linear form factor. It is not linear, longitudinal form factor, it is quadratic in temperature, and the transverse part of the form factor vanishes, but when we consider the static limit, that is omega 0 and k 0, they both are finite, and their contribution seems to be the same. What it means is probably the system has a unique web like nature to exhibit. Where we have plotted the factors epsilon minus 1 and its variations for different values of omega by k to show that there are regions for which pi t and pi l may behave non-trivially. So, for first diagram, this is the related to the pi l, and the second diagram, second graph corresponds to the value of pi t. The interesting behavior is how they behave close to omega equal to 0. In one case close to omega equal to 0, the contribution is finite, whereas in the other case close to omega equal to 0, the contribution vanishes, and the same thing happens in the asymptotic limit too. And the frequency of oscillation is, or the propagation relation, dispersion relation that follows from here is given on the line above for a long wavelength limit, that is omega square and k square relation, there is a dispersion relation. So, in the situation when omega tends to 0, you have values of k for which the whole quantity is, or there are k values when it is imaginary, and that means there is a sort of screening, and in this particular case there is at k equal to 0, there is a magnitude for omega which is held constant, and the screening mass which tells you that when in the static situation how far the fields should penetrate at high temperature. This is given by the expression that is flashed over here. The whole description can be summarized by this table, where we have given the frequency ranges when they are greater than the plasma frequency, when they are less than the plasma frequency, corresponding quantities, those are real, those are imaginary, and what is the status of the longitudinal part and the transverse part are compared side by side, and in general this describes the situation when there are no third electromagnetic constant and how the waves, electromagnetic waves behave in such a medium. Now, if one looks carefully into the values of the plasma frequency, then one would see that under the situation, under the conditions, whether temperature is less than the electron mass and chemical potential is less than electron mass, or they are both much greater than the electron mass, leads to different situations. And any attempt to overlook the situation and use the classical description that is provided to us are always fraught with some kind of what should we call the departure from the actual situation, where the magnitude of the departure would depend on the particular values that this omega p and pi t and pi l provide at those physical situations. So, this is another very important thing that needs to be evaluated, understood and addressed before one talks of wave propagation in a medium, even if it is not moving with respect to anything. So, with this we would like to conclude this section and thank you for your time and patience. Thank you.